All right, welcome back. We are going to do a couple more examples in section 6.8, still on L'Hopital's rule. And this is specifically for the forms 1 to infinity, 0 to the 0 power, and infinity to the 0 power. Okay, so let's do this example. Let's find the value of the following limit. Let's find the value of the limit as x approaches infinity of 1 plus 1 over x raised to the power of x. Okay. This is in the form. What is the form of this? That's what we should check first of all. The inside, which I might call f of x, as x approaches infinity, f of x does what? This 1 remains constant. This term, the top is constant. The denominator gets very large, approaches infinity. So that approaches 1 plus 1 over infinity, which is 0, which is equal to 1. And that's the f of x function. And g of x, which I would call this, as x approaches infinity, obviously that approaches infinity because that's just x. So this has the form 1 to the infinity, which is one of those indeterminate forms that we discussed that we have to use the following process to evaluate. So, first step, step 1, I'm going to evaluate the limit as x approaches infinity of g of x, which is x times the natural log of f of x. F of x is 1 plus 1 over x. Okay. This has the form. The form is, well, as x approaches infinity times what does the natural log of x approach? Well, we said that this term approaches 1. Natural log of 1 is 0. Therefore, this has the infinity times 0 form, still not a form that I can use L'Hopital's rule for, but I could rearrange this. I could say, well, the limit as x approaches infinity of x times the natural log of 1 plus 1 over x is equal to the limit as x approaches infinity of, I'm going to write it as the natural log of 1 plus 1 over x over the reciprocal of x, so over 1 over x. I'm going to check the form again. The form, the top we've said is 0. The denominator 1 over x as x approaches infinity also approaches 0. There we go. This is one of the indeterminate forms that I can use L'Hopital's rule for. I can use L'Hopital. Now that we rearranged it like that, we're allowed to use it. Okay, so I am going to rename my functions now. I'm going to call this function f of x These are different f of x and g of x functions than I named before. I'm going to call this function g of x. I need to find the derivative f prime of x, and I need to find the derivative g prime of x. F of x, I'm going to rewrite it as the natural log of 1 plus x to the negative 1. Therefore, f prime is equal to 1 over whatever's inside the logarithm, 1 plus x to the negative 1, times the derivative of what's inside, which is 0 plus a negative x to the negative 2 power. I'm actually just going to leave it like that and not simplify it. If g of x is equal to 1 over x, which is x to the negative 1 power, that means g prime of x is equal to negative 1 x to the negative 2 power. So I have f prime and g prime, which tells me that this limit, or rather, I'm going to go with this limit, is the same by L'Hopital's rule as the limit as x approaches infinity of the derivative at the top, f prime, which we've said is 1 over 1 plus x to the negative 1. I'm going to rewrite as 1 over 1 plus 1 over x times negative x to the negative 2 power. And that's all divided by g of x. G of x being negative x to the negative 2 power. Now you can see why I did not simplify. I can tell I have like terms top and bottom. Those will cancel, which is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x, which is equal to, this term is constant at 1, this term is constant at 1, this term will approach 0. Therefore, I have 1 over 1 plus 0. 1 over 1 plus 0, which is just 1. Okay? So that was step 1. So step 1 told me that the limit as x approaches infinity of this function, x times the natural log of 1 plus 1 over x. I used L'Hopital's rule to show me that that limit is 1. But that's not actually the limit we're trying to find. I have a second step. This means that because this limit is finite, this limit is a real number, that is the first option for this particular form. So this means that the limit as x approaches infinity of f of x to the g of x, which in this case is 1 plus 1 over x to the x power, is equal to e to whatever that limit is. That limit is 1, or just e. And that might look slightly familiar to you. We examined this limit, or one actually similar to it. Wasn't exactly the same limit, but it was similar to it, using a table way back in chapter 6. And we determined that a limit similar to this is that natural base e. So now we showed it using L'Hopital's rule. Okay, maybe let's do one more. Let's evaluate the limit as theta approaches 0 from the right of the sine of theta raised to the power of the tangent of theta. This again has the form f of x to the g of x, or excuse me, that's the function. Looks like f of x to the g of x power. So now I need to check the form, make sure it is actually in indeterminate form. As as theta approaches 0, sine of theta approaches 0 as well, because sine of 0 is 0. And very similarly, as theta approaches 0, tangent of 0 is 0. Therefore, this has the 0 to the 0 form, which is an indeterminate form. It is indeterminate. Okay. So I have to use that process that I did previously because I have a function raised to a function that I'm taking the limit of. So step 1, I'm going to find the limit as theta approaches 0, of that function in the exponent, the tangent of x, times the natural log of the function being used as a base, the sine of x. Okay? I need to figure out what the form of this is. The form of this is, again, as tangent of theta, or as theta approaches 0, tangent of theta approaches 0. So that first term will have a limit of 0 as theta approaches 0. This next term, well, the sine of theta is approaching 0 from the right. So let's see. The graph of natural log, again, looks like that. And it looks like whatever is inside the logarithm is getting very close to 0. And it's getting close to 0 from the positive direction. So from this direction. So it looks like this term, natural log of whatever is inside, will approach negative infinity. So it looks to me like this is a limit of the form 0 times negative infinity, which also happens to be an indeterminate form that I cannot use L'Hopital's rule for. So I have to rearrange this in some way that will allow me to use L'Hopital's rule. I have, let's see, how could I do this? Tangent would be the logical choice to take the reciprocal of, because its reciprocal has a definition in trigonometry. That's equal, the limit as theta approaches 0 from the right of tangent theta times natural log of sine theta, I could rewrite as limit as theta approaches 0 of natural log of sine theta over the reciprocal of tangent, which happens to be cotangent of theta. I'll just make a note there. That is because 1 over the tangent of theta is equal to the cotangent of theta. Okay. I should check the form. Okay. So let's do that. Let's check the form. We already know what the top is, as theta approaches 0 from the right, natural log sine of theta approaches negative infinity. As theta approaches 0 from the right, the cotangent of theta, I have to again refer to the graph, it actually approaches negative infinity, or excuse me, positive infinity. Therefore, this has the infinity over infinity form. I can use L'Hopital's rule. This is one of the specific indeterminate forms that I'm allowed to use L'Hopital's rule for. The top function, I'm going to call f. That bottom function, I will call g. I need to find the derivative of both of those. F prime of x is equal to, well, let's see. It is equal to 1 over the whatever is inside natural log, so sine of theta, times the derivative of sine, which is the cosine of theta, which I'm going to write as cosine theta over sine theta. And because I know what's coming, I'm not going to simplify that and write it as cotangent. But I would understand why you would naturally do that. G prime equal to the derivative of cotangent, which is negative cosecant squared theta. Okay, so I have the two pieces, which means I'm going to use L'Hopital's rule to rewrite that limit as theta approaches 0 from the right as f prime of x, which I said is cosine theta over sine theta, divided by g prime, which is cosecant squared theta. Okay, I am going to use my knowledge of trigonometry and algebra to rewrite this. See if it simplifies. This is the limit as theta approaches 0 from the right of cosecant squared is the same as 1 over sine squared theta. So I can rewrite this as cosine theta over sine theta, the top stays the same, times sine squared theta, which is equal to the limit as theta approaches 0 from the right of one of the signs cancels. So I'm left with, excuse me, I have a negative sign down here to include that. So I have limit as theta approaches 0 from the right of negative cosine theta times sine theta. Okay, which is equal to, let's see if we can evaluate it. Cosine of theta, or negative cosine of theta, is negative cosine of 0 times sine of 0. We don't have anything in the denominator now except a 1, so I don't have to worry about division by 0. This becomes negative 1 times 0, which is equal to 0. All right, that was all step 1. So let me write that down. From step 1, I've determined that the limit as theta approaches 0 from the right of tangent of theta times the natural log of the sine of theta is equal to 0. Step 2 is shorter. Now for step 2, I want to determine, well, what is the limit as theta approaches 0 from the right of the sine of theta to the power of the tangent of theta. I know that it's equal to, because again, we found a finite limit here. This is equal to e to the power of whatever that limit is that we found, which is equal to 1. So it turns out that this limit approaches 1. All right. And I think that will be all that we will do for this particular section.